All right, we're doing construct binary tree from preorder and Inorder traversal today. This is Leetcode 105 and it's a medium question. So remember, with any binary tree, before we even look at the question, you should be thinking about recursion. Let's go ahead and read the question. Given two integer arrays, preorder and inorder, where preorder is the preorder traversal of a binary tree, and inorder the inorder traversal of the same tree, construct and return the binary tree. And they give you an example here. Has the preorder traversal in a list as well as the inorder traversal in a list or an array. And then we're asked to make a tree to deal with this. So I think you'll find that in most of what you learn, you'll probably be doing this the other way around and actually constructing the nodes from this representation in a list is kind of a little bit hard to think about intuitively. So I also had problems when I approached this problem just trying to do the preorder and inorder traversals over and over again and not really understanding how that could get me the tree, because there's clearly things that are missing in both. But the general idea is that we need to use the information from one and exchange it with information for the other in order to build the complete picture. So I didn't really like this example that was here, so I'll make my own. And it's a little bit easier to see, in my opinion, what you should do, simply because this tree only has one node on the left. So that can be a little bit misleading, I think, and maybe lead you down a road you don't want. So let's just make a balanced binary tree. And I'm just going to draw it here. So remember, this is not a binary search tree. Okay, there's no search here. So you cannot assume that there's any sorted properties. That's not what we're going for at all. And it might seem obvious, but maybe working through what the preorder traversal is will help. So what is preorder? Well, preorder first is the root, second is left, and then 3 is right. Okay, so we'll deposit whatever's at the root first, then we'll go to the left as far as we can, then we'll go to the right when there's no other option available. So in this case, preorder would be 1 because we first print out what's at the root, then we go to the left, and then we print out what's at the root, 2, okay? Then we go to the left yet again, and we print out what's at the root. So that's 4. Now that this has no children, we have to go back up and to the right, and we see that what's at the right there is 5. So 5 has no children, so we're done with that. And 2 has no more unprocessed children, so we're done with that. And we're back at 1. Now that there's nowhere else to go but the right, we have to go to the right, 3. And then there is something to the left, so we're going to prioritize that first, 6. No more children, so we have to go back up. And then what is at the right here? 7. Okay, we're done with 7. It has no more children. Have to go back up, and 3 is finished. And now since both its children are finished, we know that 1 is finished. Okay, so we just work through kind of a preorder traversal. And if you are familiar with kind of coding this up, you will also find it easier to understand the problem maybe. So familiar yourself with definitely how to print out or get the preorder traversal of a binary tree. Inorder is instead going to the left, processing the root, and then going to the right. But let's just go ahead and run through this inorder traversal. So I'll use a different color so that we can see what we've processed. And this color will be red. Okay, so for the inorder traversal, we start here. Then we need to go to the left. We need to prioritize going to the left, right? And then we need to prioritize going to the left again. And we can no longer go to the left. So what do? We print out the root. Okay, so the root, so this node is now done. It has no more children. So we have to go up. And what do we do here? Well, we've already done everything to the left here. So we have to print out the 2. Now we can go to the right. All right, the right is number 3. So we do inorder traversal on that. And this is a child node, so there's nothing else that needs to be done here. This is done, and this is also done. Okay. Now, what's interesting is when we get back up here, this is, we've done everything on the left for this node. So what do we have next? We have the root. So let's go ahead and take care of that. We're going to print out the root. Now that we're done with that, we need to go to the right, right? So we go to the right. What do we have? Do we have something to the left of this? Yes, we do. So we have to go there first. And then when we're at this node, what are we considering? Okay, there's no more children. So we have to print out, there's no more children to the left. So we have to print out the root. Is there anything to the, no. So we're done with this node. Go back up. Okay, 3, we have to print out the root because we've already done everything to the left. So print out the root, which is 3, get it out, and then what's next? 7. So we finished everything here. Okay, and this is the in order traversal. So it's, yeah, so we have both our traversals and we kind of understand how they work. Now, using this example, how do you think we should go ahead and construct our original binary tree, only knowing these? And I think what helps is to realize that, or first try to do it with 1, okay? For example, the preorder, okay? What do we know from the preorder traversal? What can we say for sure? Well, we know that 1 is at the top. Because of the way preorder works, root is always first. So 1 will always be the first element in the preorder traversal, and by extending the logic, we know that the root will always be the first node. So from the preorder traversal, we know the root of the tree. We know that what this element is, which in this case, it is 1, right? So let's go ahead and take away 1. We've already solved this part of the problem. We can go ahead and make a node and call it 1. But do we know which of these are on the left and which of these are on the 2, 4, 5, 3, 6, and 7? Well, looking at our little diagram here, we know that it's these two. Let's say if I use blue for left and green for right. We can look at our diagram and we can figure this out. But there's nowhere that we know from the preorder traversal where this split is, where the split is in between them, right? We don't know from the preorder traversal how to distinguish which ones are on the left and which ones are on the right. We know that they will be together, but we don't know anything about where this pivot is. And that's the key thing to realize, is something that we can get from the in order traversal. Now, in the in order traversal, we are missing which node is the root of the tree. We don't know that it's 1. It could be easily 5. And it could be easily 6, 3. It doesn't matter. We don't know anything about what the root is. But if we do know the root, we do know what is to the left and to the right of that root. So if you look at this in order traversal and we happen to know the root, or we happen to know any node, we know what is to the left and to the right of it, simply due to how an in order traversal is created. It always has the root in the middle. So because of that, if we go ahead and use our colors here, we know that 4, 2, and 5 are the nodes on the left, and 6, 3, and 7 are the nodes on the right, to the right of 1. We don't know that 1 is the root, but from the preordered traversal, we do know that 1 is the root. So if you can imagine this, right, in our little tree that we've constructed on the left, we now know that 4, 2, and 5 are on the left. We don't know what order they are or what structure they are, but we know that they are on the left, and we know that 6, 3, and 7 are on the right, okay? And how do you think we should figure out what the structure of this is? Well, if you think about it, we've actually just reduced the problem to a smaller problem. We know that this, whatever this structure happens to be, it will be the result of making a binary tree from these elements. It will be the result of whatever happens to be the binary tree that results from this. And ditto for the right, correct? So because of that, we've reduced the problem into something that can be solved using recursion. We've made the problem smaller. The problems are the same problem, it's just that one is smaller than the other. We've reduced the size of the problem, and we can then call our same function of construct binary tree on this left and this right, and those will respectively be the left and right branches. So that should stick out to you a little bit once you've been keeping recursion in mind this whole time. Okay, let's go ahead and code this up. So remember, this is a recursive algorithm. So we need a base case. And what is our base case? Well, obviously, if preorder is empty or Inorder is empty, they should be the same size. We want to return none. It's an empty list, or excuse me, it's an empty tree. So because of that, if not preorder or not Inorder, although this is probably unnecessary because if we're doing this right, preorder and Inorder should be the same size, right? They're traversals of the same tree, but let's just go ahead and return none in either of these cases. I mean, it's a little bit unnecessary, but just to be clear, okay? And then we can go ahead and write our recursive code. No more base cases are needed. So first things first, what is the root of our tree? Well, we know from the preorder traversal that's going to be the first element. The root value is going to be equal to preorder 0. Now we need to use this information in order traversal to find out what's to the left of to the right of that. So to find where this root value is in our Inorder traversal, what we can do is use this little function called index. It's built into Python. It just finds the index of the value, in this case our root value. And now we have our pivot, okay, our pivot index. So what do we do with this pivot? Well, we essentially have everything we need to figure out what our recursive calls should be, because we have with our pivot the part of the traversal that will correlate to the left side of our tree. And we can go ahead and make our recursive calls to build tree based on our new arrays that we're going to construct here. So let's go ahead and try and figure out what this case would be for the left. So obviously we need to first make our node. We still haven't done that. So let's go ahead and do that real quick. And then we need to set the left and the right branches of this node to be the results of our recursive call. So let's do that. Some recursive call. Let's figure out what we put in that recursive call in a second. And with that, we can go ahead and write what our preorder list would be. So in this case, it's pretty simple. We know that our preorder list of our left side of the tree is going to start after the root node, but where does it end? Right? Where does it end? And our pivot actually tells us how many elements are in between the left and the right, or are in the left side of the tree. So if we go ahead and do it for example here, okay, our pivot in this case would be 3, because we would find that 1 is here in our Inorder list. So our pivot would be 3. So we also know that in our pre-list, there are 3 elements in the left side of the tree. And that's how we can partition and figure out what is the left side in our preorder traversal array as well. So let's go ahead and code that up. Now, what is our new Inorder traversal array for the left side of our tree? Well, it's simple. We just need to go up to our pivot array. Next, for the right side of the tree, and let me make sure I actually slice the correct array here, or an array, any array at all. Okay, so for the right side, what do we have? Well, it's exactly the inverse of these. So instead of 1 to 1 plus pivot I, it is 1 plus pivot I to, and the rest of the array, that will be the right side. And then whatever's not in here is going to be, whatever's not in the left is going to be in the right, excluding the pivot, right? So pivot I plus 1, and then we're good here. Then we return the root, as we always do in these recursive cases. You can see how this will work. Let's go ahead and run it and see what we get. Okay, some syntax errors. And you can see we pass the cases and it's looking good. Let's go ahead and submit. And yeah, you're going to see that it looks terrible here in terms of runtime. I mean, it's beating 50% of users. But in general, this is how you solve this problem. Now, what is the runtime of the solution? Well, there are 2 things that you can think of that might help you figure this out. First of all, each time we are running through this build tree, we are getting rid of 1 element essentially. Okay, so For example, when we process build tree once, we essentially remove this 1 from the amount of work we have to do. So now we have this and we have this, okay? So for each of these, you can know that this function will run n times. So it's n times something. Now, what is it doing in each time it calls this function or method, right? What is it doing? What amount of work is it doing each time? Well, it's a little bit hard to figure out, but the most amount of work it's doing is with this index call. Let me just tell you, this takes n time to find the index of a value in an array, as well as this slicing, which is also taking n time. So you can think of it as n plus n plus n. It's some order of n, right? So we have n iterations, and then for each of those iterations, going to take n time. So what we get is n squared. Now, is there a way to solve this? There is, but I doubt you will have to consider this very deeply in an interview. The solution to trying to get rid of this, n time, the second n time, right? So basically, we need to try to get rid of this slicing, first of all, at the bottom, as well as this taking n time. And you can do it with some complicated work. You can do it if you're pretty creative with using the indices, okay? And if you use the indices instead of slicing the array, and use maybe a hash map to try and keep track of these indices so that you don't have to find what the index is for each value, you could probably save some time there and eventually get with the O of n time solution. Again, I think it's kind of unreasonable to think of that in an interview. So this has been the how to do Leetcode 105, and I hope this video helped.